Okay, welcome. It's a great pleasure to have Ruochen Ma as our speaker today. Ruochen got his PhD in physics from Perimeter, and then he went to U Chicago, and now he's at UCSB. Uh, I learned a lot from Ruochen. We had a paper on boundary criticality together. So far, Ruochen's most influential works are about topological phases with average symmetries, or more generally, mixed state quantum phases. And the topic today is also in that direction. Ruochen, please go ahead.
Oh, thank you. Thanks for coming, and thanks for the invitation and the introduction. So today I'll be talking about what I've learned in this project, especially from these two wonderful collaborators, Shengqi and Vedika, both at Stanford University. And this is the title of my talk. And let me first motivate the talk. So in this talk, you will hear about some recent results on the following two questions. Colloquially, the first question is how can two thermal states, two systems in thermal equilibrium in the same phase be transformed into each other using operations that preserve some form of spatial locality? And secondly, using the first result, we are going to understand how should we think about topological phases like topological orders at finite temperature thermal equilibrium. So first, a introduction. So when we start condensed matter physics, we are often interested in the notion of universality, namely emergent phases at long distance often have properties that are independent of microscopic details and shared by all states within the same phase. For example, in the familiar example of two-dimensional topological order, like the Tori code, these universal properties may include topological ground state degeneracy when you put the system on a topologically non-trivial manifold, and long-range entanglement, and excitations out of the vacuum that may carry fractional statistics, the so-called anyons. And then an important question is, where does this universality come from? Why emergent phases can have so many universal properties? And for concreteness, let's look at the toric code model, the toric code example in more detail. So here I draw a phase diagram of the ground state to the toric code under some perturbation. And here I write the perturbation as a sum of local poly z, but in fact, the specific form is not that important. And for a pretty generic local perturbation, the phase diagram of a ground state toric code look like this. So whenever the perturbation is not super large, everything changes continuously until at some critical s, you reach a critical point where the energy gap of the Hamiltonian closes. And within the regime before the critical point, there is a special point, namely the unperturbed toric code model, which is exactly solvable. And you can work out basically all the defining properties of a two-dimensional toric code in a couple of minutes. I just list a few. So you can find that the unperturbed toric code model has a topological ground state degeneracy, and it has a one-form global symmetry generated by loop operators. So you have some operators supported on some, say, contractible loops whose shape and exact location can be deformed continuously while the operator always stabilizes the ground state. So this is good. And now the question is, what about the ground state of a perturbed toric code, which is no longer exactly solvable. Does it still have all its nice properties? This is the question. And for ground state, we have a satisfying answer formulated under the name of quasi-adiabatic evolution or quasi-adiabatic theorem. So the setup is basically I have a one-parameter family of local Hamiltonians parameterized by this parameter S. And the assumption is that within certain parameter regime, the energy gap from the ground subspace to the first excited state remains non-zero. So all the excited state, I don't really care. I only demand that the spectrum is empty here. And in this case, the object we want to think about is this projector onto the ground subspace parameterized by this perturbation. And the main point of this work of quasi-adiabatic theorem is that a finite energy gap along this path implies that the perturbed ground subspace can be related to the unperturbed ground subspace by a so-called local unitary circuit. More precisely, this operator US is generated as the exponential of some quasi-local effective Hamiltonian called the quasi-adiabatic continuation operator. And essentially, it is a sum of local terms. And then due to Liebowitz bound, this operator US has a finite light cone, which explains the term local unitary circuit. And simply from the existence of such a circuit connection, one can then transport many long-distance properties of the fixed point model to the perturbed state. For example, you can conclude that this perturbed Hamiltonian also have a topological ground state degeneracy, and it has a so-called emergent one-form symmetry. So basically, you can conjugate the loop operator for the unperturbed fixed point model by this local unitary circuit and obtain a slightly fattened loop operator. And this slightly fattened loop operator will still stabilize the perturbed ground subspace. And it is the generator of the emergent one-form symmetry. And then from this work, from this influential work,
may I ask a question?
Uh-huh.
Do we know what happened to the one-form symmetry at the phase transition point at the S star?
So there, the energy gap close. I think you don't have. I don't think you have emergent one-form symmetry there.
Then you're saying that the one-form symmetry operators are widened, and then what happened to these operators at the critical point?
Yes.
So they cease to be symmetric operators, but
they may not have locality anymore.
Okay, thanks.
Ruochen, just want to mention, maybe it's useful if you go back one slide. You see here, originally you have energies levels at 0, 1, 2 energies. They are all separated in energies and adding perturbation. Suppose after adding perturbation, the spectrum looks like this figure, meaning the original energy level now spreads into a band that are still separated. Then actually quasi-adiabatic continuation applies to each band.
Yes. That's right.
It's not just a ground state property.
Yeah, right. Yeah, that's a good point. Okay, so then from this work, we tend to think about this pure state or ground state quantum phases, especially topological phases, simply as equivalence classes of states that can be related by the local unitary circuit equivalence relation. So colloquially, any two pure states, they are in the same topological phase if and only if they can be connected by a local unitary transformation. And in case any of you are not very familiar with this object, a local unitary circuit looks like this. So this breakwork diagram. And by quasi-local, I mean the size of the light cone of this circuit scales as L to the 0th power. Here, L is the linear system size. It can be logarithmic or polylogarithmic due to some technical reason. But the essential point is that the size of the light cone scale as L to the roughly 0th power. And this is a very good definition physically because according to this definition, states in the same phase, they would share the same long distance asymptotic of correlations and entanglement. For example, state in the same phase would have the same long range order and the same long range entanglement, etc. And a final comment, maybe for the expert in the audience, is that this type of local unitary circuits have some local reversibility. Basically, it means that you can locally invert each gate to get the inverse of the entire circuit, which among many other consequences makes this definition symmetric and therefore an equivalence relation.
Sorry, Ruochen, in this definition, do you require the two states to be the ground states of anything?
In general, you don't have to.
Yeah, as a definition,
just any two pure states.
And then in this definition, the two states have the same correlation length.
Pardon? I think I can include some, for example, exponential tail of the circuit.
Okay. You meaning you don't consider a discrete circuit, but a continuous time evolution.
So here I use a circuit in a very vague sense. So it just means there is a finite light cone or a linear light cone.
But is it a strict light cone or can it be a fuzzy light cone?
It can be a fuzzy light cone. Okay. Okay, I see what you are saying. I want a strict linear light cone.
Then this doesn't change the correlation length.
Yes.
Yeah, then by this definition, if I consider, say, the previous example, the ground states of different toric code states in the same phase, then they are not connected in this definition.
So you want to say that a finite time Hamiltonian evolution could change the correlation length, right?
Yeah.
Yeah, I'm not sure if that's an important issue here, but for yeah, we may talk about this offline, but here I just want a strict linear light cone.
Okay, thanks.
And now comes the question, what about phases at finite temperature thermal equilibrium? So again, let's look at a concrete model, which is basically the 40 toric code model under perturbation. And the 40 toric code is famous for being a finite temperature topological order at low enough temperature. So here in the phase diagram, I include both directions. One is the temperature and the other is the perturbation. And whenever both parameters are not super large, it is in a topologically non-trivial phase. So basically, the physical intuition is that in 4D, the excitations are supported on closed loops, which cannot proliferate at sufficiently low temperature. So there is a low temperature non-trivial phase. And for the other direction, namely the perturbation, the reason is that we expect higher form symmetry breaking order has some robustness against symmetry breaking perturbation. So this is an intuitive understanding of the phase diagram. And within this low temperature non-trivial phase, there is again a special point, this zero temperature unperturbed toric model, which is again a sum of commuting projectors and exactly solvable. And you can explicitly derive the long distance properties at the fixed point. So it has a topological ground state degeneracy. It has a set of two-form global symmetries generated by membrane operators. And now the question I want to ask is this state ρ1 in the low temperature phase also have some form of topological degeneracy and some form of higher form symmetry? And in fact, before answering yes or no, in fact, at finite temperature, even make sense of this terminologies is highly non-trivial because at finite temperature, this state ρ1 is a mixed state with a finite thermal entropy density. So what is a topological degeneracy? And given the nice story of the ground state topological phases, we want to ask the following question. So is there a circuit that connecting this finite temperature state to this zero temperature ground subspace, which allows us to transport all the nice long distance properties at the fixed point to the finite temperature state? And what is the analog of a finite energy gap at finite temperature thermal equilibria? And then this leads me to the main result of our work. So for clarity, I'll present the ground state story and the thermal state story in parallel. So for ground states, the theory of quasi-adiabatic continuation tells me that whenever two ground states, they are connected by a gapped path of Hamiltonian, then there exists a quasi-local unitary circuit that connects the two ground states. And as I mentioned before, the local unitary circuit is locally reversible, and therefore it is an equivalence relation. And for Gibbs states, our conclusion is that whenever two Gibbs states, they are connected by a path in the parameter space along which a certain correlation length stays finite, then there exists a pair of quasi-local quantum channel circuits that connect them in both directions. So here, a pair of quantum channel circuit is important because in general, a quantum channel is not invertible. Nonetheless, our construction of the channel circuit does have some form of local reversibility, meaning that you can locally reverse the action of a local gate using another local channel gate locally. And this channel C tilde, you can basically view it as a product of all the local reversing gates of the forward channel. And therefore, this makes the definition symmetric and an equivalence relation. And the correlation length we introduce is a little bit special. We expect this correlation length to be finite in many non-critical thermal phases even in some non-trivial low temperature phase, including the discrete symmetry breaking order and topological order, etc. And finally, as an application, we can finally make sense of these topological properties at finite temperature. For example, we can conclude that this state ρ1 also have some topological degeneracy. And therefore, we can further conclude that a quantum self-correction or quantum memory is a universal property within an entire thermal phase. So the physical intuition is that whenever you have some topological degeneracy, then it can often be used to store some quantum information. So this is a rough overview of the main result of our work. Let me pause here and see if there are any further questions.
Hello, a quick question. So here for the existence of these channels to connecting to Gibbs states, do you have any requirements of the boundary conditions for the system?
Here for simplicity, I assume I put the system on a closed manifold. Because usually on the boundary, this correlation decay assumption would be violated in many cases.
Oh, okay, I see. So that's like a simplification, or do you really know that even at the boundary, somehow it can still work, but just maybe technically difficult?
So whenever you have a boundary, and on a, for example, on an open manifold, the assumption still hold, then it still works. The construction still works in that case.
Okay, thanks.
Hi, I have a question. So, for two Gibbs states in the same phase in your definition, is there some universality in terms of dynamics? Say they are both the steady state of some like local Hamiltonian dynamics.
I'll come back to this later.
Okay.
Any other questions? Okay, now let me introduce our definition of correlation length. So in this work, the Hamiltonian being considered is always a sum of local terms. So here I simply fix the norm of each local term to be 1, and I absorb the temperature into the definition of the Hamiltonian. And the Gibbs state is the exponential of the minus Hamiltonian. And to state our definition of correlation length, I need to define this operator algebra, which I denote as curly A. So formally speaking, it is the operator algebra generated by all the Hamiltonian terms. So it includes all the linear combination and product of all the local terms in the Hamiltonian. So for example, in a transversal field Ising model, this Hamiltonian algebra is simply the C2 symmetric algebra that is invariant under the Ising C2 spin flip symmetry. So it includes all the terms like nearest neighbor ZZ coupling, the transversal field, and their product and linear combinations and so on. And hereafter, I will call this algebra as the Hamiltonian algebra.
Sorry, just to make sure, here are you talking about the algebra or just the linear space made by these operators?
Yes, right.
Which one? The
algebra generated by the Hamiltonian terms.
So do you allow for a given Hamiltonian or for generic Hamiltonians?
I need to first fix the Hamiltonian.
Then if you are talking about the algebra, then I should allow the operators to multiply. If I multiply, I get a term not in the Hamiltonian.
Yes, sure.
Oh, okay, you include that into the
Yeah. I include all these terms generated by the Hamiltonian terms.
I see.
Their products, their linear combination, everything.
Okay, thanks.
Any further questions, since this is really important? Okay, and then I consider a tripartition of the system like this, which I'll call it as the annulus tripartition. So, so basically here, A is a finite region, and B is a buffer region that surrounds the region A and separates it from the rest of the system, which I denote by C. So A is some finite disk-like region, and B is a buffer surrounding it. And in this work, I measure the correlation using this object, which I call the covariance. It is basically defined as the supremum of operators on A. So the covariance between region A and C is defined as the supremum of the unit norm operators supported on A and C, respectively. And I impose a further constraint that this operator OA and this operator OC, they are chosen only in the Hamiltonian algebra. So this is a little bit different from the Euro definitions of covariance. And the main difference is that the operator is chosen only within the Hamiltonian algebra. Any questions?
Okay, what's the motivation of this?
You will see. You will understand soon.
Okay.
Basically, the motivation is to make this definition to continuous to work even in low temperature phase.
So if the thickness of the region B is much larger than the correlation length, then the regions A and C are approximately independent?
Yes, yes.
Okay.
So I have to first introduce our notion of correlation length, but basically that's the intuition.
Okay, okay.
And then I define the notion of clustering of correlation. A state satisfies clustering of correlation if this covariance between the region A and region C decays exponentially as a function of the distance of A and C, between A and C, basically the size of this buffer region. Here, the prefactor f is a function that grows no faster than certain polynomial of its argument. And this is our notion of correlation decay, which I call clustering of correlation. And I require it to be satisfied for any annulus tripartition on the system. If so, I call this state to have clustering of correlation. And in this work, we say a state have finite correlation length. When we say a state have finite correlation length, we actually means something even stronger. So when we say a thermal state have finite correlation length, if this thermal state and all its neighboring thermal states obtained by changing the coefficient of the local terms, maybe non-uniformly, all these near neighboring Gibbs states, they satisfy clustering of correlation. Then I say these states have a finite correlation length. For example, in the transversal field IC model, all this neighboring Gibbs state would include like all neighboring Gibbs states with slightly perturbed the temperature and transversal field. Is this clear? So I want all the neighboring Gibbs states obtained by I add some perturbation upon the Hamiltonian and to have this clustering of correlation whenever the maximal variation of the coefficient to be less than some finite delta.
So this puts the system away from any finite temperature phase transition?
So basically, it means that the state is away from a phase transition. Yes.
I have
That's
another
correct.
question. So in the definition of the covariance, you are already assuming that the operator norms of OA and OC are one.
Yes. Yes.
Then the covariance is upper bounded by 2, right?
Yes. Yes.
Then I wonder, in your definition of clustering, do you need the prefactor? After all, the left-hand side is trivially upper bounded by 2.
Aha. Yes.
So when A and C are far separated, it appears that at least within this definition of covariance, you don't need the prefactor.
That's right. But I somehow want to because the covariance here, the correlation may include, for example, connected correlation between local operator and non-local operators. I do want, for example, whenever the operator OC is highly non-local, the growth of this covariance is a little bit controlled.
Yeah, but still, if you only consider non-local operators where the operator norm is 1, the covariance is still trivially upper bounded by 2.
Yes, that's correct.
So,
Maybe I want to examine the scaling of this correlation function.
Also, a related question is, in your stable clustering of correlations, that delta beta, that's the infinity norm. So if the
Yes.
infinity norm is upper bounded by something, that means I'm not allowed to, say, change the Hamiltonian uniformly, right?
I can change the Hamiltonian, for example, uniformly.
Then,
Here, I just mean the maximal coefficient.
oh, this.
So, for example, if every coefficient is changed by 1, then this object would be just a 1.
Oh, I see. So this is not the infinity norm.
Oh yeah, this is not the ordinary like operator norm.
Okay.
Next station, Bedok.
I think there was some
Sorry, say
technical
again.
issue. I think there's some technical issues.
Okay.
Yeah, one person just unintentionally made some sounds.
Okay. Yeah. Okay, then comes some comment. So when do we expect our assumption of stable clustering to hold and to fail? So first, when do we expect it to hold? So first of all, at sufficiently high temperature, a stable clustering is guaranteed to hold. And this is probably the only provable case in the list. So it is proven in this paper. And however, due to our physical intuition, we expect stable clustering to still hold within like some low temperature non-critical thermal phase. For example, one is the discrete symmetry breaking order. You may wonder, so in the discrete symmetry breaking order, you have this long-range correlation between order parameters. Why do you still expect a finite correlation length? This is because by definition, the order parameters, they transform in a non-trivial representation of the symmetry, and therefore they are not in my definition of the Hamiltonian algebra. So they don't contribute to my covariance. And similarly, we still expect the stable clustering to hold in topologically ordered phase. And similarly, in topologically ordered phase, there are this long-range correlation for like non-constructible loop-like operators. However, due to the specific geometry of this annulus tripartition, this region A is homologically trivial. So this large loop-loop correlations, they do not contribute to my correlation length. So I expect that in a topologically order, the state should still satisfy stable clustering of correlation. And when do we expect the assumption to fail? So first of all, at phase transition, where the correlation lengths diverge. And it's actually a quick sanity check, because otherwise any two Gibbs state could be connected locally, which is certainly not true. And another example where stable clustering would fail is in the continuous symmetry breaking phase. So there, the reason is that you have this algebraic decaying of correlation due to the Goldstone boson. So our definition of stable clustering would fail in, for example, a superfluid.
I suppose in the KT phase, it also fails.
Yeah, sure.
Mm-hmm.
Any other questions?
So maybe, sorry,
Uh-huh.
can you remind me that the phase transition here you refer to are referring to the phase transition of mixed states?
Mm-hmm. Yes.
Is that defined by like if you can connect the two mixed state phases, if you can connect the two states by a local circuit or something like that? I mean, did you define this mixed state phase carefully here?
So here, there could be many definitions of finite temperature phases. For example, the free energy density being local, or if there exists a local circuit connection, and it's unclear whether the phase boundary, according to different definition, would coincide or not. Basically, I just want to say, okay, whenever this assumption holds, then we can construct this local channel circuit.
I mean, when you say you expect this stable clustering to fail, there is a phase transition,
right? Yes.
Is this just a rough reference, or you have some explicit meaning?
So here I just want to say at a phase transition, usually the correlation lengths will diverge, right? So you don't have a finite correlation length.
Okay, I see. Yeah, thanks.
And let me now briefly explain the construction of our channel circuit. So first of all, let's solve a minimal version of the problem. Let's try to change the temperature, or more generally, the interaction locally via a local quantum channel. And once this is understood, the rest of the problem is pretty straightforward. So the question is, I want to change the temperature within the local region A using a local circuit. This is the question I want to solve now. And the construction breaks into 3 steps. Let me explain it in word. So the first step is I trace out a slightly enlarged region, AB1. And I get the reduced state on the complement B2C. And then I observe that the reduced state on B2C is very similar to the correspondingly reduced state on this complement obtained from this target state, rho tilde. So basically, I want to say that the reduced state of rho and rho tilde on this region B2C, they are very similar up to some exponentially decaying error, which I'll come back later. And finally, I fill the hole. Here, this step, basically, I dig a hole. And here, I try to fill the hole using a local quantum channel that does not touch the region C. And I obtain the final state. And therefore, I achieve a local temperature variation using a local quantum channel. This is the rough intuition of the construction. Let me explain the final two steps in more detail. So the step 1b is essentially the observation that in a thermal state, a finite correlation length implies that local perturbation perturbs locally. So the intuition is basically from the imaginary time or equilibrium linear response theory. So suppose that I want to change the Hamiltonian density within the region a little bit, and I detect its influence on this region C using some operator on this B2C support on this B2C using some operator supported on this region B2C, this operator O. And I find that the variation of the operator O up at leading order of the perturbation is simply proportional to the space integral of a susceptibility, which is nothing but the connected correlation function between this detection operator and the perturbation, the Hamiltonian density. So from here, you may understand why I define my covariance only in terms of the Hamiltonian algebra. This is because the perturbation and the Hamiltonian density is within the Hamiltonian algebra. And whenever this detection operator O is orthogonal to this algebra, this formula simply gives me 0. And whenever this connected correlation function decays exponentially, then intuitively the influence of increasing or decreasing the temperature in this local region decays exponentially on this region B2C. And this intuition can be made more rigorous, but that's highly non-trivial as discussed in this recent paper. But the final upshot is that in a thermal state, a finite correlation length implies that I increase or decrease the temperature on a local region only leads to a tiny little change on a region far apart. Any questions?
Sorry, yeah. Could you please briefly explain what's the difference between the definition of clustering in here, which only uses the operators in the Hamiltonian, and the conventional definition of clustering, where I don't have constraint for the operators?
So for example, in the IC model, the transversal field IC model, this Hamiltonian density would be Z2 symmetric, right?
Yeah.
And here, this operator O then must also be symmetric, otherwise this formula gives me 0. So although you have this long-range order for order parameters, but if I define the covariance only in terms of symmetric operators, then this covariance cannot see that long-range order. Does this answer your question?
So does it mean that
so basically we
please go ahead.
So basically this definition, our definition of covariance, we expect it to have exponential decay even in, for example, Ising order phase, because we are measuring correlation function between symmetric operators.
Does it mean that you're constraining the operators that may appear?
Yes, yes, exactly.
I see. Thanks.
Ruochen, in the paper you cited on this slide, did they prove the LPPL for starting from a generic decay of generic operators or decay of the operators you choose?
They use covariance that define in terms of all operator algebra, generic operator.
I see.
But then that definition couldn't work in like low temperature phase or topological phase because of the issue I just mentioned.
Yeah.
So to make the construction to work in low temperature, we need a modified definition of correlation length.
Although in that case, it's not clear whether LPPL can be made rigorously at the moment.
No, we cannot prove that in low temperature phase.
LPPL is generically very difficult to prove.
Sure.
Thanks.
So basically, I think it can be made more rigorously only at like high temperature where the cluster expansion converges. Otherwise, I don't know any good method to prove that. And the step 1C is basically filling the hole according to the target state. Here I use the recent result, namely a Gibbs state is approximately Markovian. So mathematically, it means that the conditional mutual information between AB1 and C conditioned on the second buffer region B2 is exponentially small as a function of the size of the region B2. So physically, the intuition is that whenever this quantity is small, then the direct correlation between the region AB1 and region C that is not mediated by this buffer region B2 is small. And it turns out whenever this conditional mutual information is small, then you can recover this region AB1 only from the region B2 without touching C using a local quantum channel. And essentially the error is upper bounded by this conditional mutual information, which decay exponentially as a function of the size of the region B2.
Ruochen, can you remind us in the first relation, how does the prefactor scale with the different sizes?
You mean this one?
Yeah.
So the worst case, I think currently, so it can be exponentially large in the area of the of AB1.
I see. What about C?
So okay, the prefactor is essentially exponentially large in the minimal area of AB1 and C. So, and because here AB1 is local or quasi-local, so this is always the minimum.
Okay.
So it's essentially exponentially large in AB1. That is the worst case. But that's not an obstruction for our construction to work, turns out.
Because it's a local region.
Yes.
But by the way, when you say area, are you referring to the area of a 2D system? And in generic dimension is the volume?
More generally, in arbitrary dimension. I just want the region A to be a disk-like region and finite.
And the prefactor is exponential in the area in generic dimension.
Yes, generic dimension. And then combining these three steps, I achieved the goal that I changed the temperature locally via a local quantum channel. And basically the error is the sum of these two steps and it decay exponentially as a function of the size of both buffering regions. And once I can do it locally, I can then do it globally. So now let's solve the problem of increasing or decreasing the temperature uniformly throughout the system. And this is our goal. And the strategy is actually very, very simple. I simply implement the local temperature, many local temperature variations in parallel, as long as their corresponding quantum channel do not overlap. So for example, in the first layer, I change the temperature of all the regions labeled by 1, and I have some buffer region in between to make sure that their corresponding quantum channel do not overlap. And then the second layer, and then the third layer, and so on. And crucially, due to the assumption of stable clustering of correlation, all the intermediate states have clustering of correlation. And that enables our previous construction of local temperature variation channel to work. And this is where we need the stable clustering assumption. And it turns out that the size of the two buffer regions, B1 and B2, have to scale essentially logarithmically with the linear system size to achieve any desired global error. And therefore, the locality of the circuit that connected to Gibbs states, kind of the size of its light cone scale polylogarithmically with system size due to some technical issues. So it is quasi-local. It scales out to the 0th power. So here complete.
Sorry, I feel a bit strange here. So suppose we consider 1D system concretely, and I change the temperature a little bit. That is, I think that will satisfy the condition that delta beta is smaller than delta. Then we know in that case the correlation function, the correlation length will change generically.
Yeah. Yes.
But in 1D, I don't think this. In 1D, I think a quasi-local circuit with such depth, I don't think it will change the correlation length.
Why not?
Because suppose we start from one state and apply the circuit to the state, and now look at the for the new state and look at the correlation function of two operators, see how fast they decay. This is the same as looking at some transformed operator, how fast the correlation function of some transformed operators decay in the original state. Now the new operator, the transformed operators have a larger support. But in 1D, so the decay is set by the mutual information. In 1D, the decay of mutual information is just given by the correlation length. There's no prefactor that depends on the size of the subregions. Then this seems to suggest applying such a circuit doesn't change the correlation length. But we know it should change the two states have different correlation lengths. I don't know if there's some other errors not included at the moment.
I don't think so. I don't think I follow your argument.
Oh,
sorry.
Oh, maybe we can discuss offline.
Yeah. Then in the last few minutes, let me quickly explain how to apply the circuit connection to self-correcting quantum memory. So first of all, what is a self-correcting quantum memory? So intuitively, it is a system that when coupled to a low-temperature thermal bus, it can encode logical information for exponentially long time, essentially. And mathematically, it can be formulated as the following diagram. So I start with a logical state. I start with some logical state. And I can find an encoding channel that encode this logical state into my thermal equilibrium. And then I allow the system to evolve under thermal noise for a time t. And then I apply a decoding channel to obtain some final state omega prime. And I want the final state to be close to the initial state up to an exponential error, up to some small error epsilon. And a self-correcting memory simply means that I can find such a encoding and a decoding channel, and the memory time is large. That's basically the meaning of a self-correcting quantum memory. And theoretically, a thermal noise is usually modeled by a Lin body that describes the thermalization process in the nature. And here I impose two constraints on this local Lin body. So first of all, it is a summation of quasi-local terms. So it's a local term with some exponential tail. And secondly, each local term stabilizes the finite temperature deep state as a steady state. And an explicit form of such a thermal Lin body, of a thermalizing Lin body is constructed in this recent work. And our claim in the work is that for any thermal state, if it can be connected to a zero temperature topological code by a path along which our stable clustering assumption holds, then this ρ1 would preserve quantum information for a stretched exponentially large time. So as a summary, self-correction is a property of the entire thermal phase. So let me quickly explain the proof idea. So basically, we need to answer two questions according to the definition of a self-correcting quantum memory. The first question we need to answer is, what is the encoding and decoding quantum channel? And this is very simple. So if we identify the logical space as the, say, ground subspace of a four-dimensional topological order, then the encoding and decoding channel would simply be the channel circuit constructed above. So intuitively, I can understand this encoding as thermalizing a particular logical sector using the circuit I constructed above. And the second question I need to show, the second thing I need to show is that the encoded state is an approximate steady state of the thermalizing Lin body. And it's a little bit non-trivial, but here I'll just explain the logic in a hand-waving way. So it breaks up into several steps. So first of all, so any logical state, I start by noting that any logical state and the zero temperature deep state, basically the ground state projector, the ground space projector, they are locally indistinguishable. That's a property of the quantum error correcting code. And secondly, due to the quasi-locality of the circuit, you can show that this encoded state and the finite temperature Gibbs state, they are also locally indistinguishable. And since the thermalizing Lin body is the sum of local terms, so each local term cannot distinguish the two because they are locally indistinguishable. And therefore, if it has the thermal Gibbs state as a steady state, then it must also have the encoded state as an approximate steady state. And this completes the proof of the second part of the proof of any questions? So basically, we found an encoding and decoding quantum channel, and then we showed that any encoded state is a metastable state under a thermalization dynamics. Any questions?
So what controls the error here?
Here the error is basically the approximation error here. So our channel circuit can only approximately connect to Gibbs state.
Mm.
And that controls the error here.
Okay.
So the precision of our channel circuit have some scaling with its locality, and turns out that error also controls the evolution of this encoded state under a thermalizing Lin body. So this is basically what I want to talk about today, and some open questions. So first of all, currently we don't know that whether two states in the same phase with continuous symmetry breaking order can be connected via some quantum channel circuit that preserves certain form of spatial locality. This is an unsolved issue. And the second open question is that can we kind of replace the stable clustering assumption by a weaker or more natural assumption that only require, for example, clustering of correlation. We've done this in the paper for commuting Hamiltonians, but currently for non-commuting Hamiltonians, we don't know how to do it. And finally, are there any implications of our circuit construction for the gap and non-worst case mixing time of a thermalizing Lin body, say starting from a nearby Gibbs state in the same thermal phase? So that's another interesting open question, and I'll stop here. Thanks for your attention.
Thank you, Ruochen, for the very interesting talk. Any other questions?
Actually, I have two questions here. So first, about the locality of the constructed channel. Is it well known that the path recovery map you used can be like written as some breaks as you depicted at the beginning? Is it a common knowledge?
So here, for here, I only need the channel to be local, right? And then
So the local means it is
yes,
strictly supported in a local
yeah,
region.
it's only supported on this A, B1, B2. And then I implement many local channels in parallel, as long as their spatial support do not overlap.
Okay. So in this sense, you don't need it to be many small breaks inside the AB1.
No. So here, No, I use one channel. So because this A is a local region, right?
Mm-hmm.
I just use the local channel to increase the temperature of a local region. And for the global circuit, I use many local circuit. Many local gate to to uh, to to achieve this global temperature change. So 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 maybe here this region one and some surrounding area they are the region A, B1, B2.
I see, I see.
Yes.
And a second question is, can you comment on the stability of your constructed channel? Say, if I have three density three Gibbs states with very minor temperature difference, then is it if I want to connect them to the same final Gibbs state, is it uh, obvious that the channel you need to use will be kind of close to each other? I don't expect like you have to drastically change the channel to fit a slightly different initial Gaussian mixer state.
Mm-hmm, mm-hmm.
Is it true or not?
So yeah, I'm not sure how to measure the stability of a channel.
You can use the diamond norm.
Oh yeah, of course, but that would always, for example, uh, I think whenever for example, the global state is distinct, then I'm not sure if you want a local stability measure or a global stability measure.
Yeah, it doesn't matter. My intuition is that if I really have a quantum computer and I want to prepare a thermalized state from another thermalized state, then if I change the initial thermal state a little bit, do I need to change the whole circuit or whole channel drastically to achieve the final thermal state?
If, for example, if you only change the state locally, then the the channel far apart, I would expect it doesn't change that much. But for
Uh-huh.
example, if you change the state like globally, then each gate would be slightly different from the original gate, right?
Yes. So the error could kind of accumulate. So
Yes. Yes.
I see. Yeah.
Yeah, then I expect the error would accumulate since each gate would be different.
Uh-huh. I see. Thanks.
Other questions? Oh, I think I have some questions. Just in the
Mhm.
open questions you mentioned, in the second open question, you said for computing project Hamiltonians, you can use clustering instead of a stable clustering to make everything work. My question is, in the case of a commuting project Hamiltonian, does clustering already imply stable clustering?
No, no.
Is there any counterexample or there's no derivation?
Uh, yes, so intuitively, I would think the the clustering of correlation would have certain stability, but I don't know how to prove it.
Mhm. I'm asking this because there's a related question, which is the stability of a gap, which we
Hmm.
always assume. Suppose we start with a gapped system, then we add a little bit of perturbation, we
Hmm.
always assume there's still a gap, but it has never
Yes,
been rigorously proved. However, in the case of a frustration-free Hamiltonian with certain condition
yes,
called local quantum local topological
yeah.
order something, then it
Hmm.
can be
Hmm.
proved. I wonder whether the
Hmm.
same story also carries over here. Start for those Hamiltonians starting from clustering, then one can choose stable clustering.
Uh, yeah, we tried very hard, but we couldn't do that.
I
Yeah, we
see.
don't know how to prove.
Mhm.
But 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 yeah, indeed, from physical intuition, uh, I think stable clustering would have certain clustering of correlation would have certain stability.
Yeah. Then coming back to my previous question, I was asking, you said using a circuit with depth that's polylog of the system size, one can achieve. I think what you mean is that you can perfectly connect the two states, right?
No, I have here the locality is a function of both the system size and the desired error. So here epsilon is the global error.
I
It's
see.
basically the distance of the resulting state and the global target state.
I see. So
Uh,
to perfectly reproduce it, you really need an infinitely deep
yes,
circuit. I see. Then
yes.
then
So
then then
here
there's
we
no contradiction.
yes, yeah. So here we don't have the analog of the exact quasi-adiabatic evolution
Mm.
as for zero temperature ground state.
Mm. Okay, other questions? By the way, your definition of clustering using only the operators in the Hamiltonian algebra is actually weaker than the usual clustering, right?
Mm-hmm. Yes.
Uh,
Yeah. So yeah, yes and no. So I only include a certain algebra, but I also want the the clustering to have some stability. So
mhm,
the correlation length remains finite, even if I include some perturbation
mhm.
on the
That's the
state.
stable clustering.
So, yeah, that's the stable clustering.
I see. Okay. Any other questions? Okay, if not, I'll represent everyone to thank Ruochen for the very interesting talk. Yeah, we can
Thank
leave the Zoom.
you
Bye,
very much.
Ruochen. Thank you.